Hola a todos. Em, ya, hoy día vamos a terminar la clase sobre similitud. La idea es que terminemos la materia y ya estamos terminando el curso, ¿cierto? El próximo lunes tenemos la última prueba y en rigor el lunes siguiente tenemos el examen, que ya les he comentado, no vamos a tener un examen, sino que van a ser entrevistas individuales para todos aquellos que no se alcancen a eximir, ¿ya? Así que esta es la última clase que vamos a tener. Probablemente, o sea, tienen ayudantía este jueves y quizá el otro jueves también hagamos a lo mejor una ronda de preguntas, no lo tengo tan claro, pero ya estamos prácticamente terminando el curso, así que eh, los invito a que a que hagan todas las preguntas que quieran porque esta va a ser la última clase. Tengo un par de preguntas ahí al hilo. Preguntan, ¿al final se borra una tarea? Sí. De las tareas de programación, que son 4, ya tienen publicada la última tarea, ¿ya? Que la tienen que entregar este viernes, no me acuerdo bien a qué hora, creo que a las 8, pero revísenlo, no me acuerdo exactamente. De las 4 tareas de programación se va a borrar una, ¿ya? Pero eso es de esas tareas, no de los quizzes, no de nada más, solo de las tareas de programación. Entonces, en vez de ser 4, van a quedar con el promedio de las 3 mejores tareas de programación, ¿ya? La prueba de la próxima semana la vamos a tener en horario de clase. No tiene sentido, creo yo, no vamos a ver materia, una clase antes de la prueba. ¿Y para qué nos vamos a juntar a las 7:30 si podemos usar el horario de clase? Así que lo voy a escribir de todas maneras, voy a escribir un anuncio, pero la prueba va a ser a las 4:30, ¿ya? Canvas siempre ha tirado problemas, ustedes han visto que a veces no se ven imágenes. Yo voy a tratar de revisarlo lo mejor posible, pero obviamente la invitación es a que se inscriban en el Google Meet que vamos a tener para que puedan responder preguntas durante la prueba, ¿ya? Eso, no es la mejor herramienta, pero es la única herramienta que tenemos, así que esperemos que funcione bien el lunes, esperemos que se vean bien todas las preguntas y si no, bueno, lo vamos a arreglar durante la prueba. Con los ayudantes nos pusimos la meta de tener las notas para ustedes, ojalá el miércoles después de la prueba, ¿ya? Eso significa las notas que me faltan de la tarea 4 que tienen que entregar este viernes y la prueba del lunes, ¿ya? Cosa que ustedes el miércoles sepan quiénes se eximen y quiénes no, ¿ya? Y aquellos que no se puedan eximir o aquellos que quieran dar el examen, les voy a poner un doodle para que se puedan agendar horas de entrevista, ¿ya? Que las vamos a tener desde la semana creo que es 30, desde la semana del 30 de noviembre, ¿ya? Idealmente va a depender de cuántas personas tengan que dar el examen, pero yo creo que en esa semana podemos agendar todas las entrevistas, ¿ya? Eh, no, el examen podemos hacerlo en castellano, no. Me da la impresión que ya han sufrido demasiado con el inglés, esa es mi impresión personal, independiente que a algunos les cuesta menos que a otros, pero en general me da la impresión que es una de las dificultades de este curso. Así que ya creo que ya han tenido suficiente, todas las pruebas son en inglés, todo el material en inglés, el libro es en inglés, las clases las hacemos principalmente en inglés, así que el examen no es obligación. Si alguien se siente más cómodo hablando inglés, a mí me da lo mismo. Si alguien quiere hablar castellano, hablamos castellano, no hay problema. Eso de la parte administrativa. Al final de la clase podemos explicar mejor el homework 4. Estoy pensando, sí, de todas maneras, no sé si lo vemos al tiro o al final de la clase. Eh, Quizá veámoslo al tiro, ¿ya? Y después los voy a invitar a que estén atentos a la clase. Veamos al tiro. El homework 4, homework 4, se trata de lo siguiente. Déjenme ponerlo en pantalla.
Pero fue una consulta.
Sí.
Que en el quiz había una pregunta que no se veían las alternativas.
Sí. Yo invito a todo el mundo que tuvo problemas en esa pregunta. Me llegaron varios correos. Invito a todo el que tuvo problemas con esa pregunta que me lo haga saber, porque no todos tuvieron las mismas preguntas, ¿ya? Entonces, si alguien tuvo un problema, envíeme un correo. Y como no se podía ver, lo que hemos hecho hasta ahora es que a todo el mundo le hemos puesto buena esa pregunta, independiente de lo que hayan respondido. Pero necesito saber a quiénes les tocó exactamente esa pregunta. ¿Ya? Hubo un par de preguntas que no se veían bien. Así que el que tenga problemas, mándame un correo y lo solucionamos. ¿Ya? Um, ok, le estoy compartiendo el homework 4. Ustedes en principio ya debieran haber terminado de leer todo el material de esta unidad, de la unidad de similitud, de análisis dimensional y similitud. Por lo tanto, en el fondo, tienen que haberlo hecho para haber respondido el quiz del viernes pasado. Por lo tanto, lo que está puesto en la tarea no debiera ser ninguna locura, debieran ustedes ser capaces de entenderlo. Entonces, básicamente, no voy a entrar acá en todos los detalles, pero esto está basado un poco en el experimento en el laboratorio eh, que yo presenté en esta charla que tuve con Patricio Catalán, donde básicamente, a ver, donde básicamente había una pequeña ciudad a escala, ¿cierto? A la cual se le hace pasar una onda de tsunami. Eh, Déjenme correr esto. Anyway. ¿Cierto? Entonces ustedes pueden ver más detalles sobre el experimento acá y hay un video donde se ve la onda y pueden ver las mediciones, pero básicamente acá estamos leyendo datos de laboratorio en el punto A2, que es este punto, y en el punto D1, que es este punto. ¿Ya? Y uno puede graficar estos datos de laboratorio. No tienen para qué ver el detalle de este código, esto solo está graficando, pero básicamente lo que se ve acá es espérame un poco porque esto no se ve tan claro. Lo que se ve acá, esta es la profundidad del flujo. En azul está el punto A2, en naranjo está el punto D1. ¿Ya? Entonces se ve la primera onda como incide más o menos al mismo tiempo. Eh, En el gráfico del medio son las velocidades y en el gráfico de abajo es el momento. ¿Ya? El momento lineal medido con algún instrumento. No es necesario el detalle de cómo está medido. ¿Ya? Eh, y fíjense en la escala. Esto está medido en metros, pero aquí la máxima medición llega a 10 centímetros. ¿Ya? Las velocidades está medido en metros. Dice metros por metro, pero es metros por segundo. Perdón. Eh, y el momento está medido en metros cúbicos por segundo al cuadrado. ¿Tiene sentido esa unidad? Y acá yo les digo por alguna razón, acá yo les puedo comentar, pero esto nosotros lo modelamos numéricamente, que fue lo que yo presenté también en la charla, pero cuando hicimos el modelo numérico, no modelamos el modelo a escala, sino que modelamos esto a la escala del prototipo. ¿Sí? Si yo les hablo de escala del modelo y escala del prototipo, ¿entienden la diferencia, cierto? ¿O para alguien es medio misterioso todavía?
El prototipo es el real, ¿o no?
El prototipo es el real. Entonces nosotros hicimos el modelo numérico en la escala del prototipo, es decir, uno a uno. ¿Ya? Y acá estoy leyendo ciertos resultados en esas mismas posiciones, y acá lo estoy graficando, nada más. Entonces, si ustedes grafican esto, estos son los resultados del modelo numérico. Bueno, acá yo digo, acá se cuenta como que alguien lo midió. No es cierto, o sea, tú no puedes medir el mismo tsunami. Y le digo, y es justo la misma ola. Obviamente este es un modelo, pero da lo mismo. Básicamente, aquí tienes datos del prototipo y aquí tienes datos del modelo. Eso es lo que quiero decir. Y obtengo estos resultados. Fíjense que la escala no tiene nada que ver. Esta escala está en metros y esto está en metros por segundo. No tiene nada que ver con la escala de la medición en el laboratorio. ¿Ya? Entonces la pregunta obvia es, ¿qué tan bien está representado la medición, el prototipo, con lo que se hizo en el laboratorio, con lo que se hizo a escala? ¿ya? Y a ustedes se les pide hacer dos cosas. Primero, si se fijan, acá tenemos solo profundidad del flujo y velocidad del flujo, pero no tenemos el momento, ¿ya? Este modelo o esta medición que hicimos en el prototipo no registra o no calcula el momento, ¿ya? Entonces lo que se pide es, ustedes calculen el momento, ¿ya? Esa es la primera tarea que tienen que hacer. Y lo segundo que tienen que hacer es, ok, si yo les digo que la escala del modelo del laboratorio es 1 a 50, es decir, 1 metro, o al revés, sí, 1 metro en el laboratorio equivale a 50 metros en el prototipo, ¿ya? 1 metro en el modelo son 50 metros en el prototipo o en la realidad, ¿ya? Y les digo que se siguió una similitud de Freud. Si se siguió una similitud de Freud, entonces ustedes tienen que determinar cuáles son las escalas de tiempo, cuáles son las escalas de velocidad y cuáles son las escalas de momento. Esta es la otra parte de la tarea. Una vez que hagan eso, van a poder correr. Esto no tienen para qué mirarlo en detalle, pero si se fijan acá, por ejemplo, veamos esto. Acá estoy comparando la medición de momento del laboratorio con la medición del momento del prototipo, y los resultados del laboratorio los estoy escalando por una escala de tiempo, y acá lo estoy escalando por una escala de momento, ¿ya? Y hago lo mismo acá con las otras mediciones. Entonces, voy a hacer... bueno, y primero tengo que calcular esto, ¿ya? Entonces, una vez que ustedes calculen el momento y una vez que calculen las escalas correctas, van a poder graficar eh, esta medición con respecto a, a la medición en el laboratorio y poder ver si es que si es que conversan, si es que son consistentes. Eso. Creo que es bastante simple, creo que es bastante corta. No sé si hay alguna duda o algo que no se entienda.
Profe, yo tengo una duda. Que el momentum es velocidad por masa, ¿no?
Buena pregunta. ¿Qué es el, ¿qué es el momentum? Cuando hicimos teorema de transporte de Reynolds y hablábamos de cantidad de movimiento, ¿cómo calculamos el momentum? Lo calculamos como ρ por Q por la velocidad, ¿cierto? En términos promedio. Entonces, en rigor,
Claro, en la integral de volumen.
el integral de volumen, pero incluye ρ. Ahora, uno podría decir, bueno, acá el momento está incluyendo ρ. Cuando uno mira las unidades en las que esto está reportado, parece que no hay masa, ¿ya? Entonces, un poco los dejo a... Ustedes tienen que fijarse que esto sea consistente, ¿ya? Que tienen que determinar el momento. Como tú dices, puede ser... Bueno, no les puedo dar la respuesta, pero ustedes tienen que ver que esto sea consistente con las unidades. De hecho, en ninguna parte hemos hablado acá ni de la densidad del agua que se usó, ni de la fricción del agua, ¿ya? Ni del, ¿cómo se llama? Ni del viscosidad del agua. Hasta ahora solo hemos hablado, y de hecho cuando miran las escalas que se les pide, estamos hablando de escala de velocidad, de tiempo y de momentum. Pero no, fíjense en las unidades. De alguna manera, que es lo que vamos a conversar hoy día, uno puede tener distintos tipos de similitud, ¿ya? En función de cuáles son las dimensiones relevantes del problema. Entonces, lo que ustedes tienen que determinar es cuáles son esas dimensiones y cuáles son las similitudes que se les están pidiendo, ¿ya? Veamos la clase de hoy y quizá a lo mejor debería quedar más o menos claro qué es lo que qué es lo que tienen que hacer. Y si tienen más dudas las podemos responder después. ¿Les parece? ¿Alguna otra pregunta de la tarea? ¿O la podemos dejar para después? Ok, ¿alguna otra pregunta administrativa del curso? ¿No? De lo que sí,
Yo, yo,
adelante.
las notas, el resumen de notas, ¿lo vamos a tener disponible?
Sí, eso una vez entreguen la tarea de este viernes y una vez den la prueba del lunes que viene, ojo que la prueba del lunes pesa harto en el curso, ¿ya? Una vez que tengamos eso, nosotros vamos a tratar En rigor tenemos, no me acuerdo, creo un par de semanas para tener los resultados, pero vamos a tratar de tener los resultados el miércoles. Y una vez que tenga los resultados, como les he dicho durante el curso, vamos a escalar los resultados de todas las pruebas, de todas las tareas, para no necesariamente que la mejor nota sea un 7, pero lo vamos a escalar de alguna manera. Ya no va a ser necesariamente con la cantidad de puntos originales. Siempre va a ser al menos eso o mejor, no va a ser peor. Así que eso, yo espero tenerle las notas como notas el miércoles que viene. ¿Ya? Puede que no cumpla, pero voy a tratar de cumplir. Y ustedes con esa nota van a calcular su nota de presentación, que yo también se las voy a dar calculado. O sea, les voy a subir su nota y les voy a decir quiénes se eximen y quiénes no. Los que no se eximan pues, van a estar obligados a anotarse en uno de las horarios para dar el examen. Y de los que se eximan, si quieren subir su nota, pueden venir al examen también, cosa de ustedes. Pero sí, espero el miércoles tener todas las notas. ¿Alguna otra pregunta? Oh. Ahí. Ok. Hoy día vamos a terminar lo que es análisis dimensional. Está medio chueco esto. Brevemente, si se acuerdan lo que vimos la semana pasada. Voy a cambiar a inglés. Esta es la última clase en inglés, así que aguanten, que es lo último que hagan. Okay, so as we saw last week, let's say you have a physical problem and you have k variables that define this physical problem, okay? And you also have r dimensions. By the Pi-Buckingham theorem, you can reduce this to k minus r pi variables. Okay, and pi variables are dimensionless variables, meaning that they don't have units. Okay, they don't have dimensions. They don't have, and like we saw, these dimensionless numbers or variables are a handy way to interpret measurements or laboratory data. So let me briefly talk about what happens. Let's say that in some particular cases, let's say that k is equal to r. In that case, you only have one pi variable, right? So all your physics are going to be a function of this pi 1. And since this is an dimensionless number, what this is telling you is that this number should be constant. This is not very common. Yes?
Un question. ¿No va a ser K menos R más una pi variable?
I might be wrong, but I think it's K menos... No.
Porque si K es igual a R, habrían 0 pi variables.
Yeah, I think you're right. Yes. I think you're right. So, like so. Yeah, you're right. So yeah, so k minus r is 1 in this case, right? Yes. So in this case, you only have one dimensionless number, and this dimensionless number represents all your physical problems. That means that this number should be constant all across your experiments. This is not very common, but it could be. The other case, we saw what happens when when k is r plus 2, in that case, you get 2 pi numbers. And basically you say, okay, you have a certain function or a certain pi number which has your variable of interest, and this pi number is going to be a function of the other one. Okay, so this typically is something on this shape. So you have a couple of dimensionless numbers, or two maybe, and you can try to plot a relationship between them. This is not normally straightforward. This is not that it might be that you didn't define well your case, so your lab results don't fit in a nice line. But this technique gives you an idea of how to reduce your input. And it could be the case where k is way larger than r, let's say way larger. So you get many pi numbers. In this case, it really doesn't help you much, right? Because it gets, as soon as you have more than 2 pi numbers, then it gets complicated to plot, and it gets complicated for humans to make sense of the results. So just as before, you could have pi 2 and pi 1, and maybe have a certain line, and this will be for pi 3 equal to a certain constant. And then another line, whoop, it came back, okay. And then another line will be for pi 3 equal to constant, another constant, and so on, right? So you can imagine if you have several pi numbers, let's say 10 or so, it gets more and more complicated to make sense of the relationship between them. And this is where, like I said before, this is where, for instance, machine learning comes into help, because machine learning is really good at crunching numbers and getting relationships that are, let's say, hidden into a black box from us. But we get to train this box, so we don't care really about the relationships, but we are able to make predictions. Other thing that you can do, and is what is normally done, is that you go and simulate your problem into a lab scale lab experiment, and then you just look at the results. So you are not trying to extrapolate or to generalize, but rather you are trying to see exactly on your problem what is going to happen. And this is typical for problems or physical problems that are too complex to simulate numerically, or that you have no enough data about. So for instance, as I have told you, I work in the coastal environment, and waves are really, really complicated things. So normally, if you want to design a structure in the coast, at some point or another, you're going to have to model that structure into a physical model, into a reduced scale physical model, in order to try to estimate the real forces into the structure, for instance, or the overtop I showed you before. So you're not longer trying to get these generalizations, but you're really trying to study a particular problem, a particular phenomenon. However, there is one nice, where is this? One nice, let's say, tradition in hydraulics is that you can try to make a plot with several dimensionless numbers. For instance, those of you who follow the hydraulic path are going to see this later on, so you don't need to memorize this, but try to get the takeaway idea. This plot relates a friction factor, which is described as this relationship. As you can see, this friction factor has no dimensions, so it's dimensionless. And it measures the pressure drop into a pipe, right? We've talked about this into a schematized example. And this friction factor here, it is expressed as a function of the Reynolds number. To recall, the Reynolds number relates the inertial forces with the viscous forces. Okay, and you can see a lot of cool things here. First is that when your flow is really laminar, then you get this straight line, straight in this logarithmic plot. So all pipes fall into this laminar regime, it's called. And then when you move into a larger Reynolds number, meaning here, you're into a very let's say a very turbulent regime. You can see that these lines are more or less straight, meaning that your friction factor doesn't really change as long as your flow is larger than a certain turbulence. Then your friction factor remains more or less constant, and this is this line here, the complete turbulence line. Okay, and each of these lines are another dimensionless number. In this case, is the how is this is called, is the width, the length of the roughness of the material. You can assume that if you cut a material, it's not really smooth, but it has small wiggles, right? Small roughness, and you can measure that roughness, like a depth of roughness. And here each line compares the roughness height with the diameter of the tube. So for instance, the smaller numbers are closer to a smooth pipe, I mean almost no roughness. And these values, this is a 5% roughness, so it's a really rough tube or pipe, right? So as you can expect, the rougher it is the tube, more friction it has. So this is a typical way of representing this kind of data. This comes from laboratory data, from field data, and since you're representing this with these dimensionless numbers, you can compare them and plot them together. And this is a way to make sense of, in this case, is 3 pi numbers, but there could be more. Okay. Okay. That being said, is there any doubt? I talked about this really quick last week, so I wanted to take a few minutes before moving on. So, is there any question about this? Now we're going to get into something that I think is really cool. So let's say, like in the example before, you have a stretch of coastline, and you have certain buildings, right? And here it comes a wave. So this is the actual world. This is the prototype. And you also have this into smaller scale in the lab, right? So you have your buildings and you have this wave coming in. And this is the model scale, right? So the idea of doing model experience is that these two things are similar, meaning that results that you get in the model are going to be similar of what you can expect in the physical actual world, real world. And here comes the concept of similarity. Basically, you can split similarity into 3. It's called mechanical similarity. Mechanical similarity. Similarity, and it can be expressed as three things: as geometric, as kinematic, and as dynamic. And let me show you what this means. This is really, really straightforward. Geometric means that any distance in the prototype, let's say this distance, is going to have a similar distance in the model times a certain scale, right? For instance, if your model is 1/10, then if you have a building that it has 100 meters in the prototype, in your model is going to be 10 meters. Okay, pretty straightforward. The
¿Puedes
other
repetir eso,
thing is,
profe? Es que justo se me cortó.
yeah, so you have a scale. The key thing is that you have a certain length scale, and that it has to be unique. Well, let me just continue, but put a pin on that, because that is not exactly true. But let's say you have one unique scale. Okay, and this scale is defined as, let's say, the length in the prototype divided by the length in the model, and this scale is going to be 10, for instance. This means that if you have a building that it has a width of 10 meters in the prototype, in your model is going to be a 1 meter wide, right? And this scale is the same and is unique for all the buildings in your model. So that means that you don't have a building that has a different scale. So every geometric scale is always the same. There is a caveat, though. You can have different vertical and horizontal scales if you want, but that complicates everything. But it can be done, and it makes sense to do it under some cases. So you don't need to keep that in mind, but just be aware that it can be the case that the vertical and the horizontal scales are not exactly the same. In our course, we're going to assume there is only one scale. The other thing that you need for geometric similarity is that angles are kept the same. Okay, so if you have an angle here and then you have an angle in your model, both angles have to be the same. Okay, so we normally call this we normally call it with an E because of scala, but it could be anything. So we have a length scale that's going to be a certain length in the prototype divided by the length in the model, or otherwise. It doesn't really matter, right? And this has to be unique. So you can think of certain scale of areas or surfaces. In this case, is the surface in the prototype and the surface in the model. And if you have a certain scale for length, it's easy to show that the scale for areas is just going to be the scale for length square, right? So the same idea of the building. If a building measures 100 meters by 100 meters, then the area is just 10,000 meters. And if you have the same build, this is the prototype, and if you have the same building in the model, then this is going to be 10, 10, and the area is going to be 100, which is just 10,000 divided by 10 divided by 10, right? And the same goes for volumes. The area of volumes is going to be just the area of length to the cube, right? So this is pretty straightforward. Like this is typical. It's just a geometric compression of the physical world, right? This should be more or less easy to grasp. That's a geometric similarity. So if the model is consistently shrink into a certain scale, then you have geometric similarity. What does it mean to have kinematic similarity? Can anyone guess? Maybe this is too small. Well, kinematic similarity means that kinematic has to do with velocities and movement. So the velocities have a certain scale, and the shape of their streamlines is similar in both the model and the prototype. So let's say you have a certain streamline that goes something like that. Well, in your model, the streamline should do the same, right? If it did some crazy stuff, then you don't have a kinematic similarity, all right? But that's pretty generic, but it's easier to understand. In this case, more formally, what we have is we have a length scale, it has to be unique, and we have a time scale, which also have to be unique. The geometric similarity is easy to grasp, but you have to realize also that whatever happens in in your uh, in your lab experiment is not necessarily this. It doesn't happen at the same time or at the same velocity as it happens in the prototype in the real world, right? Uh, because you're reducing stuff. So, for instance, the wave in the flume that I just showed you in this tsunami wave, it was recorded in something like, I don't know, a few seconds, 10 seconds, let's say. But you can imagine that a real wave, a real tsunami wave, will not take 10 seconds to flood a city. It will take longer, right? So there is a time scale too, okay? And and you can imagine that from these two, you get a velocity scale, which are nothing more than the time scale, but I mean the length scale divided by the time scale, right? And the same goes with accelerations, etc. You can build from this, but the idea is that if if 1 meter in your model is equal to 100 meters in the real world, and 1 second in your model is equal to whatever 1 minute in the real world, then 1 meter per second in your model is equal to 100 meters every minute in the real world, right? So you keep this relationship, and you could compute also the scale for accelerations, for instance, or the scale for volumetric flow as it is in the book or in the slides. So now you have two things. So geometric, you have a length scale. Kinematic adds a time scale. Is this clear, or is it too complicated? And dynamic, what would it mean to have a dynamic similarity? Well, dynamic, the same as kinematic and dynamic viscosity. Kinematic has to do with velocities, and dynamic has to do with forces. So for a dynamic similarity, you need that the forces that you see in your model have a certain scale to the forces in the actual real world. All right. Now, forces, as you know, uh, really depend on mass. So basically, here you add a mass scale. So 1 gram of water in your tsunami lab model. How much mass of water does it mean in the real world? Okay, it's not straightforward. You could, for instance, say, okay, I'm going to assume it's the same, but but you could also scale it. So let me try to illustrate this. This is a very old image of a movie called Titanic that went out when I was young. And this is an image of, this is a GIF of the Titanic sinking. I know that this wasn't the real Titanic, right? So this is a scale model of the Titanic sinking. And there's actually a couple of people on top, but they were added later on with CGI. So the ship sinking here is a scale one. It's a really, really small one. Let's say it would have a meter or so. It's really, really small. Try to see, look at the bubbles here. You know, the actual Titanic measured something like 30 meters wide. So you see that the bubbles of the water are not at the right scale of the ship. I don't know if it's obvious for anyone, but I remember it struck me when I watched the movie. And I remember talking about models later on to talk about this. And what you see basically is that the bubbles are way larger than they should be, right? Because the vessel is just so small compared to the actual Titanic. So what happens here is that you're distorting. There are certain physical properties that are scale or they are a little distorted. And basically, you have to choose what are the right distortions that you want to conserve, and what are the properties that you're going to have to distort. Okay. Um, so, for instance, typically, you if you do a scale model, it's easy or easier to determine the scale, the length scale, because let's say you only have a channel that measures, I don't know, a couple of meters. So you really don't have a choice on the scale. Remember, I showed you last week. Also, I showed you a wave canal that had one-on-one waves, right? The delta flume, it has actual waves, like 5 or 8 meter waves. And they do that in order to keep this length just one. So you don't have any distortion, right? Okay, I'm being asked what could be done to make it more real. I think you mean the Titanic sinking, right? Well, that's a really good question, and that's actually what you try to do when you do scale models. What can you do to make it more real? Well, one obvious choice is to do a one-on-one model. So to have the actual Titanic, break it in half and sink it. Of course, that's pretty expensive. That's dangerous, and I don't know if that doesn't guarantee that you're going to get nice results. What are the things you could do? Well, let's think of water first. What are typical properties of water? Well, you have rho, the density, you have the friction, you have the surface tension. What else could be done? You have the temperature, maybe. Temperature influences these guys. And then you have this is from the fluid, right? And then you have the flow characteristics. You have velocities, you have flow, um, you have gravity, and then maybe you can have some other physical characteristics. Let's say the width of the ship, the length, whatever, the water depth, etc. So what can you tweak? Well, maybe you can use a lighter fluid. Maybe a lighter fluid will look more real, or maybe a fluid that has a smaller um surface tension will create more bubbles, for instance. Uh, I don't know. Maybe you could do something, uh, But also what you can do is you can just realize that there is some point in which if you reduce too much your model, some things start to play a larger role. For instance, if your model is too small, then surface tension starts to be very important. Also, turbulence has a smaller scale. You can't go smaller than that. So if your model is too small, you have fewer scales between this minimal turbulent scale and your model. So your turbulence might be wrongly represented. So always when you do a physical model, a scale model, you have a certain trade-off. Okay. And let me show you typical numbers. You've seen this. When you have a Reynolds number, you have rho dV divided by mu. You can impose that the Reynolds number in the model has to be equal to the Reynolds number in the prototype. Okay. So you could impose, for instance, that the Reynolds number in your model to be equal to the Reynolds number in your prototype. Why would you do that? You know, the Reynolds number represents the ratio between inertial forces and viscous forces, right? Meaning that this is important if you think the viscosity is important for whatever model you're using, right? And if you impose that your Reynolds number is the same in your model and your prototype, you're making a choice of the importance of turbulence or viscosity in your model. So let me do one thing. I'm maybe 20 minutes away to finish. So why don't we just don't have a break now and just power through this, and then when we're done, we just hang. Does it sound like a deal, or does anybody really need to have a break now?
¿Seguí o no?
Okay, great. If somebody needs to go to the toilet, maybe just let me know. Okay, so let's say you can impose to keep the Reynolds number the same in the model and your prototype. That means that the rho of the model of whatever fluid you're using, a certain diameter in your model and the velocity in your model divided by the viscosity in your model has to be equal to rho in the prototype, a certain length in your prototype, the velocity in your prototype, and your mu in your prototype. Okay, so this doesn't look like a lot of information, but realize that just as the tsunami lab experiment, or just as the Titanic sinking, these parameters correspond to parameters of the fluid, and they are, if you're using water, they are actually just the same, right? You could use a different fluid if you knew what you're doing, but normally they're going to be the same. So you can just discard this, right? Because they're the same values. So what you get here is, sorry, this is a bit messy, but try to follow me. What you get here is that a certain dimension in your model divided by a certain dimension in your prototype has to be equal to a velocity in your prototype divided by a velocity in your model. And if you recall from before, this is nothing more than the scale of length. This is the length scale. And this, realize, is flipped. This is the time scale divided by the length scale. So basically, by imposing that you need to keep a Reynolds similarity, you are able to relate the time scale and the length scale, right? And this is, I think, a cool thing, because it's really easy to set the the length scale, normally it's just determined. Normally you can't really do much. You know, it's going to be 100 or 150th or something like that. But the time scale, you can choose it, meaning that if your lab experiment lasts, let's say, 10 seconds, those 10 seconds, what do they mean in the real world? And depending on the scale you use, they're going to mean different stuff. Okay. Is this clear? Because this is a key step that you have to take in the homework. So I'm going to write this down here. Now, another Reynolds we've seen before, but there is another typical dimensionless number, just called fruit. Okay, and fruit relates the velocity divided by where is this? By GD. I'm sorry. Yeah, GD. Or you can also express it like this. Okay, so fruit relates inertial forces with gravity forces. What you have here, you don't need to know this by heart, but what you have here down here, this is the velocity with which a small wave propagates over a surface. So let's say you have a pool and you splash something, you throw something in it. The deeper the pool, then the wave that you generate. Let's say you throw a rock and you start generating waves, right? Those waves propagate with a velocity equals to rho to square root of gh. So the deeper they are, the faster the velocity. Okay. So fruit relates the velocity of the flow with the, let's say, this theoretical velocity of the medium. Okay. And it is a very important number in hydraulics, because it determines if the flow is able to I mean, if perturbations in the flow are able to go against the current. You don't need to know this by heart. Okay, but if you have a fruit similarity, what you're doing again is you're saying, okay, your fruit in your model has to be equal to the fruit in your prototype. Okay, and this is important because, like I said before, the fruit determines if you have a river regime or a turbulent or a how it's called, well, subcritical and supercritical regime. So it can be important for hydraulic structures, etc. So here what you're saying is that the velocity in your model divided by the square root of g and a certain dimension in your model has to be equal to the velocity in your prototype divided by rho and dimension in your prototype. Okay, here again, g is the same. You could, put everything into a rotating tank and augment your gravity, for instance. You could do it, but yeah, normally you don't. So this guy just cancels out, right? And let me just square everything. So you have the velocity in your model divided by the square by the length in your model has to be the velocity in the prototype square the length in the prototype. Okay, so from here you get Vm divided by Vp square. This is dm divided by dp, right? And from here, this is just, let me just switch. This is just the scale the length scale divided by the time scale square has to be equal to the length scale, right? Because this is length scale, this is length scale. So you get the time scale square has to be equal to the length scale, so the time scale has to be equal to root of the length scale, right? Realize that this is pretty different from this one. Okay, so the same experiment, the same results, and if you impose one condition or the other, then the time, the way you convert the time between the experiment and the real world is totally different, and therefore the velocities are going to be different. Okay, and this is normally where the choice of this condition will matter. Normally the length is really determined by your facilities, and normally mass is going to be 1, because normally you're using just water, so normally this is going to be 1. So here's where you have some room to move things around. Okay, just so you know, there are other numbers, dimensionless numbers, that can be imposed in order to have a time scale. A typical one is Weber. Yes?
Una pregunta, esto no entra para la prueba, ¿verdad?
I think it's in the book.
Entonces sí entra.
Everything that's in the book goes in.
Ok, gracias.
I have to check it, but I think it's in the book. Well, I'm about to finish this, and we can solve a couple of questions. So another typical number is Weber, that relates inertial forces and surface tension. Another one is, I don't know if it's MASH or Mach, I really don't know, which relates the velocity and a certain velocity of the medium, right? So this is the
una dudita.
compressibility. Yes.
Que todos estos números adimensionales en el fondo se mantienen como se puede hacer la igualdad prototipo modelo, ¿verdad?
Yes, you can do that. You can choose to do that, but yes. But what's your question? Or
Era eso
it's
nomás.
just yeah. You can choose to keep one of them the same in the prototype and the model, but realize that they are exclusive. You can only choose one. So, for instance, if you choose Reynolds, okay, you have Reynolds similarity, but you can't have fruit similarity, because the time scales are totally different, right? So you can choose to keep one of them, but not the other. So necessarily, when you have a scale model, something is being distorted. This is one idea that I want you to keep with you. When you reduce the scale of a problem, you are distorting something. The important thing is that you are clever enough, or that you know well enough what you're doing, to choose the right scale for your problem, right? So you don't need to learn that now and here, but you need to keep in mind this. Okay, there's a lot written on physical models, and it is a very interesting thing to do. But you need to know what you're doing. It's not as easy as just grab a small city and throw some water in it, right? So yeah, you need to be aware of the trade-offs. Anyway, and there are many of these kind of typical, let's say, dimensionless numbers: the Weber, the Mach number, the Euler number. Probably the most famous for us are the Reynolds, or the fruit. Yeah, there's also the Newton number, which is important if you're dealing with forces. You don't need to memorize this, but to understand what they do. And if somebody tells you, okay, this is, let's say, do a certain experiment, and and provide a Weber similarity. So keeping a Weber similarity, what has to be the time scale, given that the length scale is 100? You should be able to compute that, as we just did here, right? Okay, with that being said, uh, let me just show you briefly. It is in the slides. You can check it out. But basically, there is an example of a spillway. Uh, you know what a spillway is? It's a structure on a dam where water can overflow. So let's say you have a spillway and you have a physical model of the spillway. And this, I'm going to draw it just very rudely, very schematically here. And this spillway is 20 meters wide. Okay, and there is some water coming here. So basically, you have a certain water head, and there is some water flowing out. And you have a flow of 125 cubic meters per second. Okay, and they tell you they constructed a scale model of this spillway at a length scale of 1 in 50. Okay, meaning that well, 1 in 50. Okay, so the question is, determine the width and the flow rate of the model, assuming there is a fruit similarity. So you have that and you have fruit similarity. Okay, let's do it. Okay, this is really, really, really easy. So the length scale is really easy. The length scale is just 1/15. So the length, I'm going to call this L. The length of the spillway is just going to be 20 divided by 15, right? So a little more than 1. You can fill in the numbers, but it's just a little more than 1, right? Maybe let me just compute it, otherwise it's going to bug me. So it's 20 divided by 15, right? So it's 133. Okay, terrible choice because this is hard to measure, but 133. And what's going to be the scale flow? Well, we know from this that the time scale is just square root of the length scale, right? So the scale for flows, for volumetric flow, is just going to be the length scale to the power of 3 divided by the time scale, right? This is going to be the length scale divided by to the power of 2.5, right? So Q in the model is just going to be 125 times 1/15 to the power of 2.5. Okay, if somebody can compute this, that would be very nice, but this is going to be small number, right? So this is a way in which you determine the similarity between the flow and the flow in your model and in your prototype. Okay, so you need a scale and you need a certain similarity in order to compute the other scales. In this case too, so this is a given, and this you get it because this is fruit, right? And the other scale that we talk about, the mass scale, in this case is just 1, because we're also using just water, right? So if we did any computation on forces, for instance, well, the mass is just the same, right? Okay, so that was it. That was fluid mechanics. That was similarity. So before we end up, do you have any questions? Any questions about what we just saw? ¿No? ¿Ninguna pregunta? ¿Está todo claro? No sé si se dieron cuenta, pero acá está básicamente lo que tienen que hacer en la tarea. O acá está la base de lo que tienen que hacer. Así que debiera ser más o menos directo, debiera ser más o menos fácil, pero obviamente léanse el material, léanse el libro, revisen las diapositivas. Yo aquí mostré en la pizarra lo mismo que están las diapositivas, porque creo que, creo que esto había que calcularlo. Preguntan, ¿todos los tipos de ejercicios son como este estilo? No, o no siempre sigue la misma metodología. Esta es una discusión que ya hemos tenido, ¿cierto? Lo importante es que ustedes se sepan la materia. En el libro hay suficientes ejercicios. En la ayudantía pasada ustedes vieron ejercicios calculando los parámetros adimensionales. Y en la ayudantía de este jueves van a ver ejercicios sobre similaridad, similitud. Eh, no sé si son siempre iguales. En el fondo, ¿podría poner la pizarra nueva? Sí, podría poner la pizarra nueva. En el fondo, una vez que te sabes la materia, me imagino que son todos iguales. Espérate, déjame borrarle el blur. Ok. Así que eso. Ahora, yo creo que esta parte es bastante estándar. Creo también que es fácil confundirse al elegir los parámetros adimensionales. Es fácil elegir malos parámetros y de alguna manera, no es que estén malos, pero de alguna manera para llegar a estos números dimensionales del Reynolds y del Fruit, tú tienes que tener una idea de cuáles son los parámetros con los cuales vas a hacer esta repetición, ¿cierto? Para ir reduciendo el resto. Entonces, a lo mejor hay elecciones que son más felices que otras y que puede significar que uno se enreda un poco en el análisis. Y eso te le da un poco la experiencia. Entonces, yo los recomiendo, revisen todos los problemas que están en el libro, revisen las ayudantías. Yo lamentablemente no tengo pruebas anteriores, así que no les puedo pasar ese tipo de material. Eh, Eso. Y también traten de pensar ustedes escenarios, traten de pensar problemas. Yo les he dicho, si llegan aquí a la clase y plantean alguna pregunta o algún problema, yo más que encantado de trabajarlo. Así que eso. Yo creo que este capítulo, el capítulo 6, es relativamente simple, es relativamente entretenido, es más aplicado, es menos matemático que los anteriores. El capítulo anterior el capítulo 5 de análisis global, quizá también es súper aplicado, es mucho menos matemático que el anterior, y es quizá donde está la gran parte, la carne, digamos, del curso. Así que también revisen bien esos capítulos del libro. Para este jueves también les recomiendo traigan todas las preguntas que puedan. La Catalina va a preparar una ayudantía sobre esto que acabamos de ver, pero si le hacen preguntas sobre la materia anterior, ella también encantada de responderle. Es la última ayudantía antes de la prueba. Así que los invito a que si tienen preguntas, ese es un buen momento de hacerla. Además de todos los canales que tenemos, ¿cierto?, en Canvas disponibles. Así que eso por mi parte. ¿Alguna pregunta de lo que vimos hoy día, o del curso, o de la parte más administrativa?
Profe, yo
Sí.
tengo una pregunta. Sería, yo tengo que elegir o Reynolds o
Sí.
Frode. ¿Eso? Como que una de
Sí.
esas. Para resolver.
Porque los dos te dan, si te fijas, los dos te dan escalas de tiempo distintas. Por lo tanto, no es posible satisfacer los dos al mismo tiempo. Entonces, cuando tú haces una escala, un modelo a escala, tú tienes que elegir cuál es la similitud que para ti es más importante, ¿ya? Así como se los comento. normalmente en estructuras hidráulicas importa más la similitud de Freud, porque importa la relación entre las velocidades. Freud se usa en general cuando tiene flujo con superficie libre, ¿ya? Reynolds a lo mejor se usa más cuando tiene flujo en presiones, ¿ya? Flujo donde la fricción de las murallas puede ser más importante, ¿ya? Pero depende en el fondo de cuál es la física relevante de tu problema, ¿ya? En el caso, por ejemplo, del tsunami en el laboratorio, Freud es más importante y por eso, como lo dice en la tarea, esa es la similitud que se impone, ¿ya? Entonces tú tienes la escala espacial y tienes la similitud de Freud que se está imponiendo. Para otros experimentos a lo mejor será más importante Weber o alguna similitud de presiones o alguna similitud, algún otro tipo. Así que sí, normalmente solo puedes escoger una, porque distintas similitudes van a exigirte distintas escalas de tiempo.
Perfecto, gracias.
Muy bien. ¿Alguna otra pregunta? Cambié de nuevo la cámara. Igual ustedes van a ver el video, o sea, van a ver la pantalla, la pizarra en la grabación. Si no hay más preguntas, yo voy a subir esta grabación probablemente hoy día o mañana. Eso, y nos vemos ya directamente en la prueba, en la próxima prueba. ¿Ok? Ya. Muchas gracias, mucha suerte en lo que queda. Nos vemos el lunes entonces. Chao, chao.
Chao, gracias, profe.